Today, we're diving into the minds of the brilliant laureates who were just awarded the 2025 Nobel Prize in Physics. But this isn't going to be a dry lecture filled with impenetrable equations. This is a story about how humanity learned to speak the universe's most secret language. To truly appreciate why their work is so revolutionary, why it's paving the way for technologies that will redefine our world, we can't just start with their invention. We have to start with the fundamental weirdness of reality itself. We must first grasp the bizarre, ghostly nature of the electron. Forget the little planets you saw in your high school textbook. The real electron is far stranger and far more beautiful than you can imagine. Our journey begins not in a modern lab, but in the quantum realm, with a single, shimmering cloud of pure possibility. For over a century, we've been fed a convenient lie. The image of the atom as a miniature solar system, with the electron as a tiny, solid planet zipping around a nuclear sun. It's a neat, tidy picture, and it's completely wrong. In the quantum world, an electron doesn't exist in one place. It exists everywhere. It could be, all at once. Think of it not as a marble, but as a cloud of fog. This isn't just an analogy, it's the reality. This probability cloud represents the statistical likelihood of finding the electron if you were to look for it. In the denser parts of the cloud, the probability is high. In the wispy, fading edges, it's low. But until you make a measurement, until you poke it, shine a light on it, or otherwise force it to reveal itself, the electron has no definite location. It is simply a smear of potential. When you do measure it, something incredible happens. The entire cloud, spread out over a vast space, instantaneously collapses into a single, definite point. A tiny flash of light, a glowing dot on a screen. That's the electron saying, "Okay, you found me. I'm here." But the moment you look away, it dissolves back into its ghostly cloud of possibility, ready to be everywhere and nowhere once again. This act of collapse, from a wave of potential to a particle of reality, is one of the deepest mysteries in all of science. And it's the first key to understanding our Nobel-winning story. So, how do physicists describe this ethereal cloud? They don't use pictures, they use mathematics. And the language they use is that of waves. Every electron, every quantum particle, is described by a mathematical object called a wave function. Think of it like sheet music for reality. The wave function is the complete score that describes the electron's behavior. It contains all the information about its energy, its momentum, and, most importantly, the shape of its probability cloud. The peaks of the wave correspond to the dense, high probability regions of the cloud, while the troughs and flat parts correspond to the areas where the electron is unlikely to be found. This is a profound shift in thinking. The electron isn't a particle that has a wave associated with it. The electron is the wave. Its entire existence is defined by this vibrating, oscillating field of potential. This wave-like nature is not a quirky feature. It is its fundamental identity. It's why an electron can interfere with itself, like two water waves creating ripples, and why it can be in multiple places at once. It's not a solid thing. It's a rhythm, a vibration in the fabric of the cosmos, described perfectly by its wave function. Let's apply this to a simple hydrogen atom: one proton, one electron. We're taught that the electron can only exist in specific energy levels, often drawn as circular orbits or rungs on a ladder. But what are these levels? They aren't physical shelves or tracks. They are stable, standing wave patterns. Imagine a guitar string. When you pluck it, it doesn't vibrate in a chaotic mess. It settles into a clean, stable pattern, a standing wave that produces a specific musical note. If you add more energy by plucking it harder or pressing on a fret, the string doesn't just vibrate more, it jumps to a new, more complex standing wave pattern, a harmonic, which produces a higher note. The electron in an atom behaves in exactly the same way. In its lowest energy state, the ground state, its wave function forms the simplest, most stable standing wave, a perfect sphere. This is the fundamental note of the electron. If the atom absorbs a photon of light with the exact right amount of energy, the electron's wave function doesn't just vibrate more intensely, it instantly reconfigures itself into a new, more complex, but still stable, standing wave pattern. This new shape corresponds to a higher energy level. The energy levels of an atom are nothing more than the complete set of stable notes its electron is allowed to play. As these electron waves become more energetic, they also become more intricate. Just like the vibrating guitar string has points that don't move at all, these electron waves have regions of zero probability. These are called nodes. A node is a surface or a point where the wave function is zero, meaning the electron can never be found there. Let's go back to that simple, spherical ground state. It has no nodes. The electron could be anywhere around the nucleus, but jump up one energy level, and things get interesting. The wave patterns can form dumbbell shapes, like the famous 2 pecs, 2py, and 2pz orbitals. These shapes have a nodal plane slicing right through the center, at the nucleus. The electron is found in one of the 2 lobes, but never in the middle. It's like the electron has to exist on 2 sides of a room without ever being able to cross the floor in between. As you add more energy, the patterns get even crazier, with more nodes, creating concentric spheres, cloverleafs, and other beautiful, complex geometries. These aren't just abstract drawings. They are the true shapes of the atom. They are the geographic boundaries of the electron's existence, dictated by the pure mathematics of its wave function. So, when a scientist says an electron jumps from a lower energy level to a higher one, what's really happening? It's not a tiny ball physically leaping from an inner orbit to an outer one. That's the old incorrect picture. The reality is far more wondrous and instantaneous. The entire probability cloud, the electron's whole wave function, reconfigures itself all at once. It's a holistic transformation. One moment, its existence is defined by a simple spherical pattern. The next, after absorbing the right packet of energy, its existence is defined by a dumbbell-shaped pattern. There is no in-between state. There is no travel time. The electron doesn't move through the space between the 2 states. Its entire mode of being simply changes. It's like a radio station instantly changing its broadcast from a single tone to a complex chord. The wave itself transforms. This instantaneous, all-or-nothing change is a hallmark of the quantum world, and it's essential for what comes next. Now that we understand the electron as a wave, a cloud of possibility, we can introduce its most famous, most counterintuitive, and most technologically important behavior, quantum tunneling. In our everyday world, governed by classical physics, if you throw a ball at a wall, it will either bounce back, or, if you throw it hard enough, break through. It needs to have enough energy to overcome the barrier. If it doesn't, it has zero chance, literally zero, of appearing on the other side. Walls are walls. Barriers are absolute. But in the quantum realm, the rules are different. An electron, being a wave, doesn't always play by those rules. For a quantum particle, a barrier is not an absolute stop sign. It's more like a suggestion. And this is where the ghost in the machine truly reveals itself. Let's imagine the electron trapped inside an atom. The pull of the nucleus creates a potential well, like a marble sitting at the bottom of a bowl. The walls of the bowl are the potential barrier holding it in. To escape, the marble would need a push with enough energy to get it up and over the rim. But the electron isn't a marble, it's a wave. When its wave function reaches the edge of this potential wall, it doesn't just abruptly stop and drop to zero. Instead, the wave's amplitude decreases exponentially inside the wall. It fades away rapidly, but it doesn't instantly vanish. This means there is a small, but non-zero, tail of the wave function that extends through the barrier and comes out the other side. And since the wave function represents probability, this means there is a small, but non-zero, probability that if you look for the electron, you will find it on the other side of the barrier, place it should have never been able to reach. It didn't break the wall. It didn't climb over it. It simply appeared on the other side. It tunneled through. This is quantum tunneling. It's the universe's ultimate loophole. This tunneling effect is incredibly rare under normal circumstances. The probability is usually astronomically low. But what if we could rig the game? What if we could make tunneling easier? This is where an external electric field comes in. Imagine applying a strong electric field across our atom. The positively charged nucleus gets pulled one way, and the negatively charged electron cloud gets pulled the other. This distorts the atom's potential. Well, it's like tilting the bowl. On one side, the potential wall gets steeper and thicker, making escape even harder. But on the other side, the wall becomes lower and crucially thinner. The distance the electron's wave function needs to travel inside the barrier is now much shorter. As the barrier thins, the probability of tunneling through it skyrockets. By applying an electric field, we gain a dial. We can literally tune the probability of this impossible event, turning it from a once-in-a-trillion-years occurrence into something we can observe and control. This control is the key that unlocks everything. For decades, quantum tunneling was seen as a fascinating but esoteric quirk of the subatomic world. It explained certain types of radioactive decay and was a neat curiosity for physicists. But it was just that, a feature of the microscopic. But then, a few brilliant minds started to wonder, what if this wasn't just a phenomenon to be observed? What if it was a tool to be wielded? What if we could take this ghostly, improbable act of tunneling and build something with it? Something real. Something macroscopic. This is the moment our story pivots from theoretical physics to revolutionary engineering. This is the intellectual leap that set the stage for the 2025 Nobel Prize. The 2025 Nobel Prize in Physics was awarded jointly to three pioneers: John Clarke, Michael H. Devoret, and John M. Martinis. Their collective work achieved something that was once thought to be impossible. They demonstrated, with irrefutable elegance, that the bizarre rules of quantum mechanics, rules like discrete energy levels and quantum tunneling, were not just for single atoms. They showed that these effects could be engineered to appear in large, man-made systems, visible to the naked eye. They took the ghost out of the atom and put it into a machine. They didn't just study quantum mechanics, they became its architects. Their work built the bridge between the ghostly subatomic realm and our tangible, macroscopic reality, and in doing so, they laid the foundation for the quantum computing revolution. The centerpiece of their discovery is a deceptively simple device: the Josephson junction. Here's what it is. You take two pieces of a superconducting material, a material that allows electricity to flow with zero resistance, and you separate them with an incredibly thin layer of an insulator, a material that should block all electrical current. Classically, this setup is an open circuit, a dead end. The insulating layer is a wall, and no electricity should be able to cross it. But in the quantum world of superconductors, something amazing happens. Electrons in a superconductor team up into pairs, called Cooper pairs. These pairs behave not like individual particles, but as a single, coherent quantum wave. And just like the wave of a single electron, this massive, collective wave of electron pairs can do the impossible. It can tunnel straight through the insulating barrier. This flow of current across an insulator, with no voltage applied, is called the Josephson effect, and it is macroscopic quantum tunneling in action. This is where the true genius lies. The laureates realized that the Josephson junction wasn't just a quirky conductor, it was a complete quantum system in its own right. The collective wave of Cooper pairs sloshing back and forth inside the superconducting circuit behaves exactly like the probability wave of an electron trapped in an atom. It's confined within a potential well, created by the circuit's electrical properties. And just like the electron, it can't just have any random amount of energy. It can only exist in discrete, quantized energy levels. Its wave can only form specific, stable standing wave patterns. The lowest energy level corresponds to one pattern. The next level up corresponds to a slightly more energetic pattern, and so on. They had created an artificial atom, not out of a proton and an electron, but out of billions of electrons moving in perfect harmony inside a metallic circuit. If you have an artificial atom, can you control it like a real one? The answer is yes. And the tool for control is microwaves. Remember how a real atom absorbs a photon of light to jump to a higher energy level? This artificial atom does the same thing, but with microwave photons. By firing a precisely tuned microwave pulse at the junction, with the exact energy difference between two levels, scientists can kick the circuit from its ground state to its first excited state. A slightly different pulse can bring it back down. They can finely tune the electric fields to make the tunneling barrier thicker or thinner, adjusting the energy levels themselves. They gained complete, deliberate control over the quantum state of a macroscopic object. They weren't just watching the quantum world anymore. They were pulling its levers. This precise control over two distinct energy states is the dawn of a new era in computation. In a classical computer, a bit is a simple switch. It's either a 0 off or a 1 on. There is no in between. But this artificial atom, this superconducting circuit, is a quantum system. Its lowest energy state can represent a 0. Its next energy state can represent a 1. But because it obeys the strange rules of quantum mechanics, it can also exist in a superposition of both states at the same time. It can be 30% a 0 and 70% a 1, or 50/50ths, or any combination. This is the quantum bit, or qubit. This ability to exist in multiple states at once is what gives quantum computers their mythical power. A computer with just a few hundred qubits could, in theory, perform calculations that would take the fastest supercomputers on Earth billions of years to complete. And the Josephson junction became the most stable, scalable, and controllable way to build one. So, how do you use these qubits? You write information onto them using those carefully crafted microwave pulses, putting them into specific superpositions. This is the encoding step. Then, you let them evolve and interact with other qubits to perform a calculation. To read the result, you perform a measurement. This forces the qubit to make a choice. Its delicate superposition collapses, and it falls into either the definite 0 state or the definite 1 state. The probability of which outcome you get depends on the superposition it was in just before the measurement. By repeating the calculation many times and measuring the statistical outcomes, scientists can deduce the answer to the problem they were trying to solve. Through this delicate dance of control and collapse, of writing and reading, abstract quantum principles are transformed into tangible, operational computation. Let's pause for a moment to fully appreciate the philosophical magnitude of this achievement. We're talking about a circuit, etched onto a silicon chip, perhaps the size of your thumbnail. It's made of billions upon billions of atoms. It is, by any definition, a large, macroscopic object. And yet, when cooled to near absolute zero to maintain its superconducting state, it behaves with the pristine, textbook purity of a single, isolated atom. It absorbs and emits single photons of energy. Its state is described by a single, coherent wave function. It exhibits quantum tunneling. It's an artificial atom, built by human hands, that perfectly obeys the fundamental laws of quantum mechanics. It proved that quantum isn't a synonym for small. It's a set of rules that can govern systems of any size, as long as you can engineer them with enough precision and isolate them from the noisy classical world. This is the heart of the Nobel-winning achievement of Clarke, Devoret, and Martinis. They took quantum mechanics from the chalkboard and put it on the circuit board. They proved that the universe's most fundamental rules were not confined to the esoteric realm of subatomic particles, but could be scaled up and engineered. They gave humanity a toolkit for building with the laws of quantum reality. They demonstrated that we could construct complex systems that behave as single, coherent quantum entities. This discovery wasn't just an advancement in physics. It was the creation of a new field, where quantum physics, materials science, and electrical engineering all converge. They laid the practical, experimental, and theoretical groundwork for the entire field of superconducting quantum computing. The legacy of this work is all around us, and it's growing every day. The Josephson junction and the concept of artificial atoms are the undisputed building blocks of the leading quantum computers being developed by companies like Google, IBM, and Rigetti. These are the machines that promise to revolutionize medicine by designing new drugs molecule by molecule, create new materials with unimaginable properties, break current encryption standards, and solve optimization problems far beyond the reach of any classical computer. Beyond computing, These ultra-sensitive circuits are used in detectors that can measure the tiniest magnetic fields, leading to new brain imaging technologies and instruments that can probe the furthest reaches of the cosmos. The impossible leap of quantum tunneling has become the engine of 21st century innovation. So we end where we began, with the ghostly act of impossibility. Quantum tunneling, once a mysterious, almost mystical effect confined to the heart of an atom, now powers some of humanity's most advanced and hopeful technologies. The journey from understanding the electron as a simple cloud of possibility to building a macroscopic circuit that thinks like an atom is a testament to human curiosity and ingenuity. The deepest lesson here is one of perspective. The rules of reality are not always what they seem. What appears to be a solid wall at our scale can be a porous boundary at another. The key is to never stop questioning, to never accept that a barrier is truly impassable. By embracing the counterintuitive and learning to speak the universe's native language, we can learn to build with its magic. We can learn to make our own impossible leaps. So, I leave you with this question to ponder. What other impossible ideas in science today might just be the building blocks of the technology that will define our future? Let me know your thoughts in the comments below. Thank you so much for joining me on this journey through the quantum world. I wish you all the very best of health and a future filled with wonder. If you enjoyed this exploration and want to dive deeper into the mysteries of our universe, please consider subscribing to the channel and turning on notifications.